Hi, I'm Ben-Yaakov. This presentation is entitled Coupled Inductors in PWM Converters. It actually deals with the question whether inductors can share the same core. There are a number of switch mode converter topologies that do have two inductors or more. An example is the Sepik converter, in which we find an inductor at the input and then an inductor at the output. And those are required for proper operation of the converter. The question is whether these two can be actually wound on the same core to save space and to optimize the circuit. Another example is a forward converter with a number of outputs. Here is one winding, there is another winding of the transformer, but then we have an inductor per output. And the question is again whether these two can be wound on the same core. Before starting to handle the question of inductor on the same core, let me say a few words about a coupled inductor. That is an inductor that is wound on one core, here's the core, and we have in this particular case two windings, this one and this one. There is a major difference between a transformer and a coupled inductor that has to be emphasized in order to see the differences between them. Although they two sort of look alike from the outside, they really are two different devices. There is also a difference that usually doesn't show up when just looking at the element, and that would be the permeability of the core, which in inductor usually the permeability will be much lower. But this is not the subject of this discussion at this point, but rather the fact that the inductor is storing energy. That is, if you have only one winding, you can feed in current and store energy in the core. This will be entirely different in the case of a transformer, in which by definition, when you have a current coming in, say in this winding, it will come out of the other winding such that N1 I1 is equal to N2 I2. Now this does not hold in a coupled inductor. It may, but usually it does not, because the difference stored as an energy, which is, according to this equation, states that the energy will be the difference squared times L over 2. In the case of a transformer again, the element is transparent as far as energy goes. The energy goes in is the energy that comes out, except for some energy that is stored for the magnetization of the core, which is not the subject of our discussion here. Okay, so we understand that a coupled inductor is basically two inductors which are wound on the same core, and that each one of them, when you look at each one of them, you see an inductor, and then the currents need not to be according to this relationship of a transformer. Another question is, what about the voltages? In this respect, the coupled inductor is really very similar to a transformer. The reason is that you have one flux that is flowing here, and the two windings see the same flux. Now the voltage seen is N times d phi dt, where phi is the flux and d phi dt is the rate of change of flux. And this is true for each winding. That is, V1 is N d phi dt, but then this will be N1, and V2 is N2 d phi dt, and of course these fluxes are the same because it's the same core. Consequently, we find, so if you divide these two equations, you find that V1 over V2 is N1 over N2, which is, of course, the relationship that we have for a transformer. which is in this respect the same thing. Okay, so now if we connect a voltage at a given time to a winding or to part of the inductance L1, this voltage will impose a certain dφ dt at the core. That is, phi will start rising because phi is the integral of the voltage. If at that time I'll connect a voltage per this2 is equal to N2 over N1 times V1, if we'll connect this voltage, then the core will not see the difference because it already has this rate of change started, let's say, by V1. So as we understand is that if we have two inductors, we can impose a voltage on each of them as long as they obey this relationship. Another point to remember is that the inductance is proportional to the number of turns squared. So the ratio of the two inductors, when you look this side or if you look this side, the ratio will be the ratio of the number of turns squared. And this is important to remember because when you wind the inductors, you have to know what type of inductances you are supposed to get. Let's have a look at the Sepik converter. Now the Sepik converter has two inductors, and the key question is, of course, whether these two inductors see the same voltage. Then you can in fact wind the two inductors on the same core. A key element that you need to decipher first is the voltage on the capacitor. Once you know that, it's very easy to analyze the circuit. Now we can find out the average voltage on the capacitor by looking at the average voltage here. Let's call this Vy, and this point here Vx, the average voltage. Another key information is that the average voltage on an inductor must be 0 because the rise of average current is equal to the average voltage times the inductance. If you assume steady state, the average current is 0, so therefore the average voltage must be 0. So let's have a look at L1. Average voltage here is of course Vin, it's a DC. So this average voltage Vx, or the average voltage at the point Vx, must be also Vin. Average voltage here, the ground side of L2 is 0, so the average voltage of Vy is 0, and we have now that the average voltage on this capacitor is in fact Vin. We now have the key information that we just go on and find what are the voltages on L1 and L2 to see whether they are indeed the same, and if so, they can be wound on the same core. So we know that the capacitor is now charged at steady state operation, and if it's a large capacitor, and we of course neglect the ripple voltage on the capacitor now, we don't talk about that, we just assume that it's practically constant. And now we look at the point Vx, and let's do it as a function of time. So we have here the switch turning on. This will be the period, this will be the on time, this will be the off time, and of course the duty cycle is T on over T, this is T, and this will be D on, and D off is similarly T off over T. Now if we look at inductor L1, we see that during the on time, that is when the switch is short, we have a voltage of this polarity. Let's call this a dot just to make this is the positive side, so to speak, so that the voltage on L1 is getting here to V1 during the on time. Now during the off time, the switch is off, non-conducting, and this point here sees V in plus diode, which I'm neglecting. V the diode is assumed to be 0, which is incorrect for low voltages, but at this point I'm just neglecting it. And of course V out. So we have V in plus V out. On the other side we have V in, so therefore the voltage is actually V out, or minus V out to be precisely, because it is plus here and minus here. Now, and this will be for the off time. Now what about L2? Well, when the transistor is on, this transistor S is on, Vx, this point is ground, this point is ground, the L2 is subjected to the voltage of the capacitor, which is, as we know, V in. So let's call this point plus just to make it the same. This will be actually plus V in if we define the voltage of the L2 like this. So during on, we have V in here, this is V in, and this will be during the duration of T on. When the transistor is off, this is during the T off time, oh, here it is, here, of course we are subjected to V out, or the inductor is subjected to V out, and as we define the dot here, this is the positive, so to speak, side of the inductor, then we have minus V out. So as you can see, the two inductors are indeed exposed to exactly the same voltage. So if we wind the inductors on the same core, there shouldn't be any problem. There are some residual problems that I'm not discussing it here, like leakage inductances or ripple, but in principle, or from the theoretical point of view, you can indeed wind two cores on the two winding. You can wind the two inductors on the same core. Now what about the inductances that you'll see? Now you'll have one core, the voltages are the same. Let's call this one V1 and this one V2, and they are flipping simultaneously and exposing the two sides to the same voltages. If the voltages here are the same, and since the voltage is N dphi dt, and since dphi dt is the same, this implies that N, that is the number of turns for V1 and V2, must be the same. And therefore, L1 and L2 will be the same. So in this case, we are going to have two inductances of the same value, same number of turns, one on the same core. Let's move now to the forward converter. We have again here two inductors. In this case, V2 and V3 out may not be the same. That is, V2 and V3 may not be the same. However, since they are driven by the same switch, the same transformer, the duty cycle must be the same. That is, we are going to see here voltage, say like this. This is the, call it V2 peak here. And here we're going to see another voltage, which is V3 peak in general, which might be different than V2 peak. Duty cycle, though, is the same. V2 out will be V2 peak times D on, and V3 out will be V3 peak times D on 2. Now, at each given point in time, there is a voltage imposed on the inductor. Let's see what are these voltages. For L2, during T on, we're going to see here V2 peak on one side, and then we're going to see, of course, minus V2 out on the other side. So this is the difference between the two, or the voltage of L2 during T on is V2 peak times 1 minus D on. Obviously, for L2, we're going to have the same thing, 3. This will be V3 peak, 1 minus D on. Now, V2 peak and V3 peak are related by the number of turns N2 and N3. So the voltage now imposed on VL2 and VL3 during this will be T on, will be like N2 times some constant. This will be N3 times some constant. So the ratio is of VL2 to VL3 is N2 over N3. So we're going to have the ratio of the voltages on the inductor are as N2 to N3. Now this is also the ratio of the output voltages, because each of the output voltages is this V peak times D on and the same T on, etc., etc. So we find also that the ratio between V2 out and V3 out is also N2 over N3. What does all this mean? It means that during T on, the ratio of the voltages is N2 over N3, and during T off, that is when the switch is non-conducting and current is flowing this direction, and neglecting D1, D2, and this should be D3, neglecting the voltage on them, the voltage imposed on the inductors is V3 and V2 out, which are also related by the same ratio. What we have in here is somewhat a different story. The voltages of the inductors are not the same, although they have the same shape during on-off, but they have the same ratio. So VL2 over VL3 in each phase, that is during T on and T off, is like N2 over N3. When we put two inductors on the same core, our goal is to make sure that the V, the T is the same. So for inductor 1, we have, inductor 2, N2 dphi dt, and for inductor 3, we have N3 dphi dt, or dphi dt is VL2 over N2, or dphi dt is VL3 N3. What this actually means is that the voltage per winding of each of these coils must be the same. If the voltage per winding must be the same, then it implies that for VL2 we'll need the number of turns N2 which are proportional to V2, and in the case of N3 the number of turns is proportional to L3. All this goes back to the transformer requirement that V1 over V2 is N1 over N2. What this said is that you can have the two inductors on the same core if you will make the number of turns of the coils for each of the inductors, the ratio of the number would be like N1 to N2. So in this case, we are not going to have the same value of inductance because the number of turns is not the same. In fact, in this particular case, we are going to have a ratio of N2 over N3 squared. That is, for example, if V out is say 5 volt and the other output is 10 volts, you will have the ratio of the inductances 1 to 4. This is not too bad, in fact, because normally when the higher the voltage, you like the higher the inductance to attenuate the ripple. So this sort of, from the engineering point of view, is not a contradictory requirement. So to summarize, there is the possibility of winding two inductances on the same core. What one has to watch is that the voltages will be the same, and once the voltages are the same, then the core really doesn't see the fact that you have two or more voltages imposed on it, because the phi dt is the same if indeed the voltage per turn is the same for each of the windings. This brings me to the end of this presentation. I thank you very much for your attention. I hope you've found this presentation interesting and useful. Thank you.